talks need to be grounded in examples, I apologize in advance. Yes, yes, yes. Okay, if you count that as an example, specialized to Eilenberg-MacLane spectrum, then yes, I will say that. I'll even what? Okay. So what are we trying to do? So the goal is to study Floer theory, but replacing ordinary cohomology by a generalized cohomology theory. Like K-theory or Bordism or something like that. And the problem is that for Lagrangian Floer theory, which is somehow the center of the subject, then we don't, you don't start with Lagrangian Floer homology group. If you're very optimistic, you'll start with a Lagrangian Floer chain complex, but even that is not true. What you really start with some kind of curved A-infinity algebra on the cochains of the Lagrangian, with whatever coefficients you're using. So there is no way to proceed with this theory unless you start by understanding what it means to take curved A-infinity algebra on your cochains if you're working over some generalized cohomology theory that is not ordinary cohomology. Now, it is a classical and well-known fact in algebraic topology that the only generalized cohomology theory that is computed by a chain complex is ordinary cohomology. Okay? So there is nothing interesting if you're going to stick to chain complexes. But fortunately, people have kind of worked out the correct analogy. So the right thing to do is, first thing to do is to replace. First, need to replace the chain complexes over a ring, and I'm going to say just over Z for now, okay, by some appropriate notion of some other kind of category, where we can do homological algebra. And then this category exists, and it's called the category of spectra. I'm not going to say much about it, SP. So maybe what I will say is that it is you start with topological spaces, and on base topological spaces, and there you have suspension, and then you can think of the category of spectra as some kind of universal thing, universal category with a map from the category of topological spaces, and so that this functor of suspension becomes invertible, becomes an autoequivalence. But for me, what I want to do is basically do algebra in it. So in order to do algebra in it, I need to know that there is a model for this category, which is symmetric monoidal. And with the usual notions, with good notions of projective and injective objects. I guess in this tech, people usually say, cofibrant or fibrant. And this model exists and has existed in literature for quite a while. So the technical words are you can either use symmetric spectra or orthogonal spectra. But somehow it doesn't really matter at the level of detail of this talk. Now, since this is monoidal category, we can therefore make sense of algebras in here or rings in here. So yeah, so orthogonal spectra is Mendel and May And this one is due to Schwede and Shipley. And there is a paper with, which I mean, if people want a reference, probably the best reference is there is a paper with, I mean, for this point of view, okay, let me just say one thing. I said there's a universal point of view. The best reference for the universal point of view is Lurie's work. So I'm going to put that here. And the best reference for kind of comparison of these models and understanding that ultimately it's all the same stuff, and it's the same stuff as just a variant of what's taught in algebraic topology courses. There's a paper with all 4 of these authors. Okay. They just wrote down the comparison between the models. So we can consider, since it's symmetric monoidal, we can consider associative / commutative algebras in here. Actually, to do the commutative ones and get the desired answer most easily, better off working in orthogonal spectra. And these are called, well, so just in some terminology, these are what I call associative spectra and associative ring spectra. Associative ring spectra. So that, and again, obviously, commutative ring spectra. And what I want to say, just before moving on a little bit, is that I said we want to do generalized cohomology theory like K-theory and cobordism, and the whole point is that your favorite cohomology theories are actually all in here. So Bordism and K-theory, and of course ordinary cohomology, and of course stable homotopy theory itself, stable homotopy. Okay. They all give us commutative ring spectra. So that's kind of a safe place to. I mean, this is maybe we're going to think about things in here. So we're going to fix some k in here. Okay. So now, given such a k, which is going to be my ground ring, this is going to be our ground ring. Okay. Like we do chi category over q or z or something. That's going to be our ground ring. We want to understand what does it mean to take a curved A-infinity algebra over K. And good. So first I'm going to do a toy version. And the reason to do this toy version is, well, I've already used 15 minutes. So let's start with the toy version, which is algebras, so curved algebras over K double brackets T. Okay? So instead of doing some base, which is more general, I just want to look at this simplest possible one-dimensional situation. This is the same K. This is the same K. I'm going to fix the commutative ring spectrum for the rest of the talk. And we want to understand what it means to have a curved algebra over this thing first. Okay? And then because if you want to do Fukaya categories, you want to do it in families. Okay, so another way to say this works, and I'll say it at the end, but in the middle. This works if you're looking at symplectic manifold with like an integral cohomology class. Okay? Yeah, it feels like it, and yet somehow it's some important point. Yeah. So. Okay, so what's a curved A-infinity algebra? I'll just remind people. So a curved algebra. So recall. So I'm going to say this case of ordinary ring. Sometimes you can just say that this is kind of discrete. So when we're doing kind of ordinary homological algebra, I'll say the k is discrete. Okay, so if k is discrete, then we can define a curved algebra over K double brackets T to be well, just to make my life simple, a free K double brackets T module. T is a formal parameter. Yeah, so this is just power series in T. A free module, let's just call it V, with operations mu k indexed by from k equals 0 to infinity, satisfying, well, they use some kind of quadratic equation. Sum of mu, let's do identity I times tensor mu k tensor identity j times, I guess I plus j plus k minus 1. This sum is equal to 0. This is kind of some kind of quadratic equation in the mu's. And so this, you could do this, but that would be kind of a silly idea. We kind of know that if you impose this, if you don't impose any additional condition, then the theory of curved algebras is not useful. So you want to impose one additional condition with the property that mu0 vanishes mod t. Okay. That somehow there could be a mu, in fact, there could be a mu1 and a mu2 and a mu1 and mu2 and so on and so forth at t equals 0, but mod t mu0 vanishes. Okay, and if you don't require this, then they don't have morphisms, because when you take f0 into morphisms. Yes, that's right. Things would blow up. You're absolutely right. Okay, so this is what, and I forgot, and there are some signs. Okay, that I'm not going to write down. So, what's the problem with turning this into something about spectra? Well, first of all, there is a sum. Okay, this is the kind of formula that does not make sense in the category of spectra. And then also there are these signs here, and that's the kind of thing that doesn't make sense in the category of spectra. Okay, so you have to find some other method. And if we don't have mu0, we know exactly what to do. We can just consider instead some kind of operatic point of view. So there is the stash of operad. Let's call it R. Okay, and you can arrange it actually so that it's just, it has spaces Rd, where d is greater than or equal to 2. Okay, and it's trivial for d equals 1 and d equals 0. And okay, so you can think of this operad in different ways. In symplectic topology, the easiest way to think about it is to take the moduli space of disks with d plus 1 mark points. But you can also think about it more combinatorially in terms of trees, planar trees. Yes?
So is there a problem with just extending this opera?
I'll do it.
Infinitely many operation, one for each tree,
If you did,
number of inputs?
yeah, I will do that. I will explain exactly how you do this, and then it'll look, yes, just, yeah. Again, for this toy version, that basically works. So, okay, so planar trees with d incoming leaves. And of course, the theory of modules over this operad is exactly the same as one as the theory of ordinary A-infinity algebras. So now I get to what Paul wanted me to say. But in fact, you can easily extend this to the curved setting. Okay, but to do it in the curved setting, I'm sorry, I'm going to replace this d by a k, otherwise I'm going to get in trouble later. To do it in the curved setting, you just want to be a little bit careful. So what you can do you can introduce some kind of operad. Let's call it C. Okay, in topological spaces, just like the stash of operad. Okay, but you're better off saying which is graded by the natural numbers. Okay, So that means we're going to have spaces like this. So, okay, and K also in N. Okay. And yeah, it contains 0.
So that K has nothing with this big spectrum.
So no, this was. Do you want me to use another letter? Can you? Okay. No, it has nothing to do with that. So yes, so this includes natural. Yeah. Okay. So what is this? So you can think of it as a cubical complex with cells indexed by planar trees whose vertices are labeled by the natural numbers. By n. Okay? But now you have to be a little bit careful. So you allow univalent and bivalent vertices, but only if the label is non-zero. This is completely natural from the point of view of Floer theory. So you only allow so vertices labeled by elements in the skin, let's call them d sub v. You only allow d sub v equals 0 if the valency of v is greater than or equal to 2. Okay? So all I'm trying to say is that if I restrict this to the d equals 0 part, so the operad d equals 0 is just well, it's basically the usual Stashev operad with its cubical decomposition. Stashev operad with its cubical decomposition. 3. Thank you. Sorry, I was thinking in terms of incoming leaves. With its usual cubical decomposition. I'll draw it right now. So for example, C0, 2 maybe, so maybe 3. This is going to be an interval. Okay, but then its interval is subdivided. And what's basically happening is that this is this one, and then now the way I label things, this whole thing is an interval. This thing labels an interval, and this thing labels another interval, and they're glued together in the obvious way. And if you do the next one, you get this. I'm very bad at drawing. Yeah, something like this.
So your D and K are probably related to your trees in some way.
So I can say, yes. Sorry, I didn't say this, but so K is exactly like there, the number of incoming leaves. Okay, so here the number was 3. This D, it is the sum of D sub V, where D sub V are the labels of all the vertices. Okay? And when, of course, when you look, whatever I said, there's a cubical complex, which means there have to be some gluing maps. Those gluing maps correspond to contracting edges. When you contract edges, you add the labels of the vertices. Somehow. I will not come back. Let me come back to that later. This is part of the issue, which is. Let me come back to that later. No, it is not the genus. Yeah, the D is again. So what you should have in mind is that if you're symplectic, let's say if H2 is of rank 1, D is the class of the degree. Okay, but so this was the case that we're all familiar with. But of course, there's other ones. For example, so now I'm going to do C1, let's say 0. This is actually non-empty, okay? And it has a single tree that looks like this and has a label 1 in it, okay? And I could continue this Oh, I said there would be no examples. Okay. So, but you could easily continue this pattern. Okay. Questions? Okay. So there is this operand. This is an operand in topological spaces, and the thing that I use that we can use is that whenever you have an operand in topological spaces, there is a functor from spaces to spectra called sigma infinity, but it's a horrible name. Okay, so I do not like this thing. I like to call it chains. Okay, so what so the chains on a space, if with coefficients in k, should be thought of essentially as the spectrum associated to it by taking sigma infinity, spectrum. So there is a functor in here, so that tells us chains on C is an operand in spectra. And now we encounter a small problem. Okay? Yes. It is obtained by grafting trees along, so there are inputs and outputs. And so I can do it. So there is a map there are 3 different maps from this one times this one. Thank you. I should have said the following thing. There are maps C D1 K1 cross C D2 K2 to C D1 plus D2 K1 plus K2 minus 1. Actually, there's not one such map. There is, let's call the map circle I. There is one such map. Well, okay, I have to decide which one is input and which one is output. Let's say for I, 1 less than or equal to I less than or equal to K1. Okay, so what is this map? This map is you take the first tree, you take the second tree, and you graft them. Okay, you just glue them at the edge labeled I. Okay? Yes?
What's C star?
It's the chains. It is the thing formerly known as sigma infinity.
Okay,
so
it is sigma infinity.
It is sigma infinity. I will not use that notation. Yes. Okay? And if we're working over K, I would have this.
It is basically a unique continuous function.
But it's okay. But it's okay. No. That's not. I wanted to call it the chains because you want the analogy with what you're doing when you're working with with discrete coefficients. Okay. So really, probably here I'm doing the chains of x with coefficients in k, which exactly means sigma infinity of x plus smash k. Okay. It's just the same thing. Okay. So this is.
In that case, yeah, C star script C is an operand in K modules.
That's right. It would be, so you're absolutely right. So if K, yeah, so in general, so this is if K is the sphere spectrum, otherwise, so I usually write mod K in mod K. And that's, again, assuming K is commutative. Okay. So this almost works, and the thing that you should object to are degrees. Okay? The problem is that the operation mu0 should have degree -2. I mean, I'm using homological grading. Okay, and it does not. The way I set it up, it has degree 0. Okay, but you have this extra variable d here, so you can just artificially shift by -2. So solution, and again, this is a bad solution. This is again, well, I don't know. Okay, so artificially shift. CDK by -2D. Okay? And you can just implement this, in the language of spectra, you smash with s to the -2D. Okay? And then things are exactly in the right degree. Okay.
I agree with that this operatic composition has degree 0.
Yeah, so the operatic composition has degree, yes, with that degree the operatic composition does not change. So these remain in the correct degrees, they're just spaces, and this one goes to -2, and then the next one, well, anyway, it goes to the right thing, it goes to -4 and everything is okay. So, sorry,
Usual chain complex cases we shift degree by 1, and the composition has degree 1.
No, because in the usual chain complex the composition is, so this composition is just saying you consider what is the degree of mu k composed with mu j. Well, that's exactly this is additive does that make sense? So the composition does preserve degrees. I mean, there's something else going on, which is the differential, blah blah blah. But the composition just preserves degree. Okay. So yes.
The only reason you stabilize was because of the expectation that u 0.
That's right. I mean, right now. Okay. So this looks bad. Yeah. But there's a much better model where you don't have to do this. Yes.
Is this some notion of like bar construction?
Yes. Yes. I will now.
Bar construction is kind of problem with algebra, not algebra disappears.
So I will now say what happens at this stage. So now, once we have this, so let me call the resulting operad O. So let O be the resulting operad. Okay. So now, if you have an operad, then you can make sense of what it means to take an algebra over it. So we have a category of algebras. We don't need the whole category. So we have a notion of an algebra of an O algebra. So let A be such an algebra. And given an O algebra, we have a notion of a module over O. And a category mod A for each such algebra. Okay. So what is an algebra? Let me just remind you just a little bit. In algebra, we have some kind of maps, O, K, and again, yes, I apologize. We need to be careful. So we really have a notion of an n. So now O algebra, which is graded by n, which is n graded. Okay. But then when I take modules, I want my modules to not be graded. The modules are not graded. Again, you could ask me, why am I doing this? Okay, because I have in mind what I want to do for Floer theory, and I'm quite sure that this is the right thing. Okay, so what does it mean that you have a graded O algebra? It just means that you have something like this. You have some kind of O, D, K, okay? Tensor, but I'm going to write smash, A, and then you need K inputs. To the, well, okay, I do it like this. A, D1, smash, blah, 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 smash, A, D. Oh my, horrible. Okay, let's do an E here. Okay, there should be E of these. Oh, E inputs, okay. And this should have a map to A, D1 plus. I'm sorry, this is a K. Good, things are okay now. dk plus E. Okay?
So A is a spectra with this map.
A is a spectrum, okay, or a K module, okay, and it is equipped with these maps, okay. And now maybe at this stage I should give some indication of what you should have in mind, okay. So the simplest idea is that, if we're doing Lagrangian Floer theory, A of D is just And again, so A of D is just cochains on L. Okay? Okay? And you should think of it as the component. So if, let's say, no, that's fine. So you should think of it as the component, the T to the D component of cochains on L, tensor K, and now I'm going to put polynomials in T. Okay? And the reason I can take polynomials in T is because I've separated out all the, there could be infinitely many operations, but I'm keeping track of them one operation at a time, so this is completely reasonable to do it. Okay? And if you think about what Floer theory would do, this is exactly what you would get. You would write down this algebra, and you would have these operations, and they would preserve this degree. But abstractly, there is no reason to assume that all of these are the same. Okay? Okay? And once you have an algebra, you have a notion of a module, and it works out more or less the same way. You have a map from A, O of K tensor, some power of O smash, sorry, A, O smash some power of A smash M to M.
When you're doing the Floer theory, you're thinking now of moduli space of all dimensions?
Yes, definitely. Yes. And so that is actually something that we'll have to go into how you handle this mod K. But right now, yeah, all dimensions. But again, because of this artificial shift, you should think that something must be off, and you can deal with that. For example, instead of cochains here, you should really shift these cochains by the Maslov index of the corresponding class, because this is some kind of H2. This parameter space should really be some kind of H2. And again, at the end, if I have time, I will say something about it. So now, what I want to observe, that modules over A have a canonical subcategory, admits a subcategory. Come on. Which I want to call mod A0 of modules which are pulled back via the projection from O to the usual A-infinity operad. So this is the usual A-infinity operad. And what does this projection do? This projection sends everything for D not equal to 0 to 0, which kills all spaces for D not equal to 0. Okay? And at D equals 0, it's just the identity map. Okay? So what is the intuition for that subcategory? Well, it corresponds to the modules over K double brackets T would support at the origin. So this corresponds to modules.
Sorry, what means it's the operand you replace module by one entries?
Yes, that's right. Yes. Your left modules, the last one, for example, you call M.
So when you say that the module is a pullback, does it mean that all A with K,
Yes.
all D greater than 0 just get deleted?
Vanish identically. Okay? So that's the pullback.
Yeah, so it's notion of what is specific to this operand because it's general categorical notion of module or but in relevant functions like.
Yeah, it depends. You can formulate a notion, general notion of modules over an operand, which will recover left modules over algebras.
It will be by modules.
It depends. It all has to do with how you deal with the ordering.
Yeah.
If you do not impose this kind of cyclic ordering, you can just get left modules without any problem. Yeah, if you put this symmetry, then it's harder to extract the left modules. Okay, correspond to modules over K double brackets T with support at 0.
You don't just support which are unrelated by T. Support means
Thank you.
Everyone would be happy if you said push forward.
Yeah, well, except possibly the speaker. Sorry. Okay. Okay. So now you get to finally definition for what we want. which is that we want to define the category of branes associated to A. I don't know if that's the best word to call it, or curved, I don't know what to call it. So the branes of A are the quotient category. Mod A, in which you kill this guy, mod 0. Okay? So this is somehow, okay, this is the, now we have some possible thing which could be conjecturally the category of some subcategory of the Fukaya category over K with support on L. So the conjecture, so for appropriate, and I'm not going to be precise here, appropriate L and K, okay?
Sorry,
Yes?
this kind of definition looks like you want to know that we're set theoretically supported. I mean, I don't know.
By some power of T.
Oh, did you write some power?
No, I did not write some power.
I mean, I don't understand what's stable here and what's not, but of course, if you use the system, it's set, you're trying to write down something like matrix factorizations. Right?
Yeah, as a quotient.
Those will roll with you.
Yeah,
Yeah, not T, but
some power of T.
yeah, so then it's set theoretically. Yeah.
Which is,
I mean, if it's not set theoretically support, it won't be stable.
no, this is what I want. Yeah. Okay.
Does that correspond to the broad non-core parameter?
Yes, that's somehow the point. Okay, you want so sheaves on a variety. You want to, if you kill the stuff that is supported set directly along the divisor, then you get things which are live in the complement, and that's what we want here. Okay, for appropriate L, there is exactly one of these things. Curved. So there is an A algebra with underlying spectra. I think I wrote it over there, but anyway, A of D, which is just the cochain L with coefficients in K, so that this branes, so let's just call it brane A, so that brane A is a, well, let me just say Floer theoretic invariant. So, I mean, it's really, you should really think of it as is the category of objects, the subcategory of the Fukaya category with objects supported on L. Of course, we don't have any other definition of this Fukaya category, but yes.
You like to replace cochains by chains and base loops.
Yes, I do like to do that.
Yeah.
Yes, maybe not for this talk. I do like to do that, and you could do that, but somehow then this statement becomes slightly different. I don't expect it to be the usual Fukaya category. And with that, there's almost no conditions on L and K. You could just always do it if you do that replacement. Subcategory of the Fukaya category with support on K. Okay, and this is something you can, again, and under some restrictive assumptions, like if you assume that, as I said earlier, that some kind of H2, that the homology class is integral, I believe we could actually verify that this would recover the usual Fukaya category over the rationals. Okay. So expect to recover the usual Fukaya category. Maybe something a little bit larger over K equals, well, let me just write Q, okay, over the rationals.
So I mean, in that case, it is an object is not just a Lagrange summary for, but something like an infinity module over.
And that is exactly what we do here, right? So the objects of this thing, the branes, are not Lagrangians. They are an object of the category of modules over this algebra. Okay? So some of those modules are going to correspond to bounding cochains on the cohomology. Some of them are going to correspond to bounding cochains on the cohomology with coefficients in some flat vector bundle. But some of them are not going to do that. Some of them are going to be more general objects.
And
Okay.
this process to this cube, this
Yes.
thing, usually you can work with lambda 0, like without any problem.
You could, yeah, you could work with lambda 0 here too, and you will get all the.
Yeah, so you don't need to quotient.
If you want the version of the Fukai category that's over lambda 0, you just work over in mod A. You don't need to quotient. You don't need to quotient.
Yeah, so that quotient is necessary if you want to find something.
If you want Hamiltonian invariance. Yeah, if you want to prove, so for example, one of the conjectures is if I take L and I take a Hamiltonian isotopy, then there will be a func or bimodule, okay, between these categories of branes, which is constructed just like in your book from the intersection of the pair and which induces an equivalence. But it induces an equivalence only after you mod out by this, because over lambda 0 it's not true. Okay, so how much time do I have? 15 minutes, great. So, so at this stage, this is fine, but I highly doubt that we would be able to prove this with this model because of how artificial this suspension by -2 is. Okay, so it just doesn't. It is not going to interact. This should be thought of as an artificial shift, and it's not going to interact well with the geometry. So what we need is a better model. Maybe this is 3. Okay, so I was talking about something which is graded by n. And really, we should work with, we should take the area, pairing with omega, as a map from H lower to R, I mean, let's say with Z coefficients to R, okay? And then you should consider the following monoid, which is the monoid of things on which this is non-negative. And let, gamma, and this is going to be fixed for the rest of the talk, be the monoid. Abelian monoid, is that what it's called? On which omega, pairing with omega, is non-negative. Okay? And so what you want to do is run exactly the same story. And you can.
Monoid is submonoid of H2.
Submonoid of H2. Okay? So you want to run exactly the same story, which means that you want to consider.
You don't assume that this image is good?
No. I mean, I'm going to say something. I mean, no, I do not want to assume this image is discrete, because that's not true in general.
Yeah, but if you just restrict to something represented by disks, then the image is good.
Well, by Gromov compactness.
Yes.
Right, but I do not want to build this in at this stage. I will impose it later.
Okay.
I mean, you will see it appearing later.
Okay.
But at this stage, no, I do not want to do that. And I think that would be dangerous, because if I did that, and then I did some isotopy or change of J, then that would change, and I would have to analyze what happens when it changes, and I do not want to, I want to set it up at the beginning. Okay. Yeah.
Maybe H2 is like pi 2?
I could do pi 2, yes, absolutely. And in fact, I had some idea, yes, that's right. Which is,
that's
no, it is not abelian. Yeah, it's okay, you could do pi 2. You could do pi 2, there's nothing wrong with pi 2. Yeah, it's non-commutative monoid. Yeah. So in fact, yes, we could try to do that, but not right now. Okay, monoid on which, okay, so now we consider, well, we want to consider now, construct a gamma graded operad, but this is very easy. So the operad in topological spaces, which is graded by gamma, with, so the space little, so C little gamma K, okay, what is this? This is a cubical complex of planar trees with vertices labeled by, labeled by our lattice gamma, such that the sum of the labels is this thing. Okay? Sum of labels is little gamma. Okay, I know this is unreadable, but okay. So this is exactly like before an operator in topological spaces. And then then you want to turn it into an operator in Spectra, and you realize that what you want to do does not make sense. So you cannot. You can do it. You can just take this. You say, I'm going to take the suspension spectrum, or the chains suspension spectrum of this. That will be an operator in topological spaces, but it is not the right one. Maybe that's the point to make. It is not the right operator. And the reason, one way you can tell it's not the right operator is you cannot make these artificial shifts anymore. You cannot say, I'm going to shift by minus d. What is d? You only have this gamma. You don't have a natural number by which you could possibly shift. Okay. That's somehow not the problem. Okay, the Maslov class you can build in, but it's still not going to be the right thing. Yeah, so the Maslov class is not an issue. I mean, you should shift by the Maslov class. Okay, but that still will not solve your problem. It still will not give you the right answer, because for Maslov class 0, you need the operation degree minus 2. That's essentially why. So you cannot artificially shift. And the way to see that you cannot do it.
So now I'm a bit confused about variance.
Variance with respect to what?
I mean, no. Sorry, you're thinking of the spectra, and the homotopy groups of your spectra will be what?
The homotopy groups. Okay, the homotopy.
Homology versus cohomology.
Well, how did I set it up? I mean, so
set it up as a module over the Stashev operator.
Chains. Yes,
Chains.
yes, that's right.
So there should be a cohomology.
That's right. Yeah. I mean, in order for the expected answer to work out, you should assume that L has some kind of Poincare duality over K. And I would just assume that. I'm going to assume that L is K oriented.
Because you said minus 2.
This one also has a. Anyway, I mean, this means nothing. This is just a formal symbol. Cochain LK is just some formal symbol right now. So, yeah. The homotopy group, the functions from L to K. And the homotopy groups of this in degree minus K will be the ordinary cohomology in degree K. So this is not. Okay, so you cannot artificially shift. And to see this, e.g., let's just imagine that you have some element. We have, let's say, gamma, in gamma, with two different primitive factorizations. Factorizations. Let's say gamma equals, let's say, G1 plus G2. And let's say this is H1 plus H2 plus H3. Okay? This one would tell you, these were really primitive things, which is more or less what we were doing before. This one would tell you should shift by minus 4. And this one should tell you should shift by minus 6. That's not consistent. Okay? So this doesn't work. Okay? But the solution, in fact, already exists in ordinary homological algebra. So the solution is to...
Sorry, so when we did it before, we shifted what by what?
We shifted the things of degree d by minus 2d. The operations of degree d by minus 2d. Which is, roughly speaking, we said the ones of degree 1 are just the primitive ones, and everything else you basically shift by how many, what is the length of the maximal way of decomposing it into smaller pieces. It doesn't make sense anymore for general monoids. There'll be another problem that's even worse, but let me just, so this is the issue in some sense. This is what doesn't allow you to shift. So the solution is to use Koszul gratings. So let me remind you that the degrees of the operations in A-infinity algebras are, again, with these conventions, with homological conventions, the degrees are minus 2, minus 1, 0, 1, 2, 3, 4. Okay? So the usual degrees of the mu k are well, okay, I'm going to do it like this, otherwise I won't be able to write the formula. This is k is equal to this for 0, 1, okay, 1 minus 1, 2, 0, 3, 1, oops, and so on, okay? Okay, but you can shift, you can always shift by k minus 1. So you can shift to the following degrees. Okay? And these are the Kuzel gradings, Kuzel graded degrees. Okay, so why is this better than this? Okay, so if you think in terms of spectra, okay, anything which lives in positive degree is a space. Okay, anything which lives in negative degree is not a space. Cannot come from a space. It must come from something which is like the dual to a space, functions from a space to the sphere spectrum. Okay, so this is some kind of mixed object. Whatever you do, in order to construct it, you must do a construction at the level of spaces and then fix it. Now, it would be really nice, and I think it is possible, to do it as some kind of Tom spectrum. Okay? But that's going to make your life very hard. This, however, is supported entirely in negative degrees. So this looks like the dual to a space. Okay? And in fact, we have a space, this one. Okay? So we could try to take the dual of it. But the dual of it will not work, because it turns out these spaces are essentially contractible, and you're not going to get the interesting homology classes. But what you could do is you could do the homology Rel boundary. Okay? So you define the boundary of C gamma k. Well, again, this is some kind of cubical complex. This is the union of all the strata which actually arise as compositions. Okay, and then you could then you can introduce. You look at the relative cochain. So take cochain's Rel boundary of C gamma k. Oops, cochain Rel boundary, okay, with coefficients in this spectrum. Okay, so now you need to shift this by 1. So I'm going to do, sigma minus 1. S minus 1 smash k. Okay. So this will be our spectrum. This will be defined to be O gamma. Okay. So you could say, how is this? So it claims that now these are the spectra of some graded operad. How is it a graded operad? Well, I'm not going to go through the details. I will just say you have boundary homomorphisms, okay, in cohomology, in cochains, and there's exactly a shift by 1 to make those boundary homomorphisms have degree 0. And so those boundary homomorphisms are what define the structure of an operad. So these are the underlying spectra. Thank you for letting me know that my time is up. Underlying spectra of a gamma-graded operad. Okay, and so then that's what we want, and the claim is that gamma-graded operad is the curved operad in this setting. So the last thing I will say is, why did this? There's actually two things I should say. Okay, so one. So the reason we were succeeded in not using this in the case of natural numbers. So the toy case worked for the following reason. It worked because of Poincaré duality. This Poincaré duality gives an equivalence up to shift between, an equivalence between homology and relative cohomology. And relative cohomology for manifolds with boundary. Okay, and the cubical complexes that arise when you're doing the case of natural numbers are manifolds with boundary, but they are not manifolds with boundary in general, and that's the first problem. Okay, the second problem, and this is what Kenji was mentioning, is that actually, if you were to think about this monoid, it is infinitely divisible. Okay? So in practice, this gamma, the gamma that appears there, I mean, if the map is not, you know, the image is not, if this is not a rational map, the class of omega is not rational, gamma may be, may have, maybe, I'm going to say infinite, I can't say. The infinite divisible is not the right word. Element of gamma may be decomposable in infinitely many ways. Gamma may be decomposed in infinitely many ways. Okay, that in turn implies that in these complexes are in fact acyclic. O gamma k is acyclic. Okay, but it's okay because it is filtered. It is naturally filtered. Okay, so the way we resolve it is we say we don't look at all modules over this. We look at things which maybe we should call gapped modules. And for gapped modules, you can write down a completion of the Hom space, which takes into account the filtration on this, okay? And then that gives you the non-trivial, let's say, curved modules, which we expect to give us the analog of bounding spaces with bounding cochains. Okay, I'll stop here.
Question?
Yes.
Base chains?
Yes.
Isn't there is a parametric inequality which guarantees finiteness for?
That's right, that's right, that's right. It's absolutely, there's no problem doing everything that I said with base chains, the chains on the base loop space. Again, the only thing I want to, that is in fact the canonical module that you should do. You should replace this H2 by some pi2, okay? And as you said, with this conjugation. And then this the canonical modules is basically the space of maps from a disk to M. Okay, but that's not quite right. What you want to do is some kind of Tom spectrum of that, because you want to twist by the degree of this by the Maslov index, and the Maslov index may not be trivial, so it's not just a suspension. So it's really like a suspension by a bundle, virtual bundle. Yeah.
How do you do this symmetry points?
Symmetry point. So that's hiding in this statement of for appropriate k. Okay. So right now we know that this works for. Okay, so this would be another story. But what you would want to do is you want to, right now what I know works is you could fix one of the Morava K theories, okay? And you could look at spectra which are local, okay? So for example, you take like mu, okay? And then you could look at what happens to mu when you try to localize it to one of the Morava K theory, you get something which is a huge coefficient group, and that would work. Yes?
So the order homology, what is used is something like a fundamental chain of
Yes.
circuit cell.
Yes.
So it is not a cycle, but it's a kind of relative cycle. Right?
That is exactly what this is.
Okay.
That is exactly what is used here. Instead of thinking about, you know, Stashev associahedron as you just homology classes, you say I'm going to switch to relative cohomology, and then there are fundamental classes here of the right degree, and I shifted stuff so that things would be easier to handle.
Last question. If not, let's thank Mohamed. So let me just make two quick announcements. There is a welcoming party at 6 p.m. in